After testing the application on the base deployment to make sure that it works, the OscarP tool can then be used to profile it extensively, given the resources specified as candidates, considering different loads and different configuration. And from the data collected by this profiling campaign, we can then generate the machine learning performance model. Doing this is particularly important for the edge devices, which are in a sense the weaker link of the applications. They have limited performance, they also cannot scale that well as opposed to the cloud, and are in general the bottleneck of the application. Doing this without AI Sprint means that the application manager has to deploy multiple infrastructure, test the application on different combinations of these candidate resources, and he also has to vary the configurations of the machines between one test and the other. Then at the end, he also has to collect the logs manually, process them, and organize them into dataset, which are then used to train the performance model. With AI Sprint, instead, it's sufficient to create a configuration file, declarative, that explains how the application should be tested, and then the OscarP tool can be launched with a single command, AI Sprint profile, and everything else is automated, so the deployment of the infrastructures, their setup configuration, the monitoring of the test, and also the collection of the logs, the creation of the dataset, and the training of the model. Everything start to finish is automated. For the demo, we consider the mask detection application, where each component can be deployed on either M4 X large or M4 large AWS EC2 instances. In the demo, I'm gonna show the structure of the OscarP directory, an overview of the input file, and the execution of the OscarP tool. Inside the project directory, we have an OscarP folder where we can put the input files, in this case is a test video, and the configuration files for OscarP. In the configuration file, we have different sections. The first one specify the input files needed to trigger the application. The test can be either asynchronous or synchronous. If the test is being done synchronously, we can specify different intervals with varying throughput specified in requests per minute and different durations. In the component section, we can define for each component an array of parallelism level, which are the maximum number of instances that a component is allowed to have running at the same time. For each value in these arrays, a test is going to be performed. The tool can be launched from the AI Sprint Studio image with the AI Sprint profile command. When starting, the OscarP tool is going to list all the configurations that are going to be tested. It will deploy the infrastructure if they are not already up. This infrastructure will be cleaned from the remnants of past execution, so services, all services will be removed, the buckets will be removed or cleaned, and then it will configure it for the current test by deploying the correct services. It will then proceed to move the input file according to the specification of the configuration file to trigger the execution, and then it's just a matter of waiting for the execution to complete. Skipping to the end of the test, the tool is collecting the logs from Oscar and also from Kubernetes, and all the information inside these logs will be processed, generates a dataset with information on the runtime and the response time of the components and the application, and at the very end it will generate the results in terms of datasets and graphs. To generate the machine learning performance model, it is sufficient to tweak out the configuration file for the ML library with the techniques that we want to use. We can now set in the OscarP configuration file the flag train models as true, and when relaunching the campaign, OscarP will notice that the data is already there, so it won't start from scratch. Instead, it will skip straight to generating the machine learning models. Now the library will automatically train different models, one for each technique. If HyperOpt is enabled, it will also use that to fine-tune the parameters, and at the very end it will test the generated models to figure out which one is the best, and it will return that.
We tested the Oscar P component on the mask detection application using a private cloud with 9 virtual machines to represent the cloud side and a cluster of 4 Raspberry Pis Model B to represent the edge cluster. The first component, blur faces, was tested and profiled on both clusters, while the second component, mask detector, was only profiled on the VM cluster. The data collected during the tests were used to generate and evaluate different machine learning-based models exploiting XGBoost, ridge regression, decision tree, and random forest. The main feature we considered is the parallelism level, which denotes the maximum number of available cores for all the services. Since all the components are single core, this is directly translated to the maximum number of components that are running concurrently. These are the results we achieved when testing the interpolation capabilities of our models for the single services. As you can see, the mean absolute percentage error is quite small, reaching at most 10%. We built an additional model to predict the execution time of the full workflow. On the left, we see the results achieved when training this model on data collected for the full workflow, while on the right, we see what happens when combining the models trained for the single services to predict the whole application execution time. We note that even if the accuracy is lower, the mean absolute percentage error is still lower than 20%, thus acceptable in practical scenarios. Finally, here we report the results on extrapolation. In the plot on the left, we see the data collected when considering a variable number of input videos. When we combine the two best models for the individual services and perform extrapolation on the data from the last test, including 20 videos, whose results we report on the right together with the corresponding predictions. The mean absolute percentage error of the combined models is 9.75%, proving the good extrapolation capabilities of our tool.